Firstly, we will discuss the basics of GANs. Then we will deep dive into its functionality. And lastly, we will find out about the business uses. Generative Adversarial Network was first introduced by 6 brilliant scientists. 3 of them you can see right now. It should be pointed out that papers explaining similar concepts can be found back in 90s, but the 2014 paper was the most well-written, the most detailed, so we should give these guys credit. This paper became motivation for many other articles, and please remember these faces because we will see them at the end of the presentation as they are fathers of GAN, or are they? We will find out. Um, okay, to fully understand the idea and geniusity behind GAN, first we should discuss the difference between generative and discriminative algorithms. Generative algorithms model actual distribution of each class, while discriminative algorithms model decision boundary between the classes. Both try to do the same thing, learn conditional probability, but generative models learn joint probability distribution firstly, and then use Bayes' theorem to find conditional probability. Last but not least, generative models are usually supervised, while discriminative models are usually unsupervised. Of course, this can change depend on the task, but this is the general overview which allow us to understand the subject more deeply. Okay, to simplify the ideas previously described, let's see this slide. The task is to find gender of the person on image. Firstly, we have data that we use to train generative and discriminative models. Then we input the test data to get the answer regarding the gender of the person on the image. Even though the output will be same in ideal world, the approaches for finding out gender is totally different. Generation model will create image of woman and men and choose the gender based on the similarity between the input data and created data. On the other hand, discriminative models already knows difference between images with men and women and can output answer based on the properties found in the image. Okay, that is the general overview of discriminative and generative models. Now let's get into the interesting part, which is generative adversarial network. And as Jan LeCun said, this is the most interesting idea in the last 10 years in machine learning, and I totally agree with him. Firstly, we should point out that there exists a probability distribution describing the kind of data we try to generate. If there is no that kind of distribution, it is impossible to replicate the data. And the generative model is unsupervised learning problem, as we discussed in the previous section. Although a clever property of the GAN, generative adversarial network for short, architecture is that the training of the generative model is framed as a supervised learning problem. GAN is made up of 2 parts, generator and discriminator. Discriminator's task is to distinguish between real and artificial data, while generator tries to create fake data that will be so close to the real one that discriminator will not be able to tell which one is artificial and which one is not. So if you have zero-sum game in the head right now, you are absolutely correct. These 2 components try to maximize opponent's loss while minimizing their own, and usually the sum of the losses are 0. This slide displays simple architecture with a black box approach. Both generator and discriminator are usually models in the family of deep neural network. Both discriminator laws and generator laws can be used for backpropagation or their combination. And there exists quite a lot of approach for training discriminator. This is really important task because we will find out that convergence is important for every neural network and especially for GAN. So my favorite approach to train discriminator is alternating training. The discriminator trains for 1 or more epochs, then the generator trains 1 or more epochs, and the process repeats. This allows us to analyze both components' performance in real time. Even though it seems simple, we should remember one thing. As the generator improves with training, the discriminator performance gets worse because the discriminator cannot easily tell the difference between real and artificial data. If the generator succeeds perfectly, the discriminator has 50% accuracy. Of course, depend on the task. In some case, there might be 33 or similar. So this progression poses a problem for convergence for the GAN as a whole. The discriminator feedback gets less meaningful over time. And if the GAN continues training past the point when the discriminator is giving completely random feedback, the generator starts to train on jank feedback and its own quality may collapse. For GAN, convergence is often a fleeting rather than stable state. And now you might understand why it is important to analyze the GAN's performance in real time and know when to stop the whole process. This is the simplest explanation for this architecture, but we can say that we know everything about the general GAN, and we are ready to understand the real working side of it. GANs try to replicate the probability distribution, as we said previously, that there should be some kind of probability distribution that we try to replicate. They should therefore use, so GAN should therefore use loss function that reflects the distance between the distribution of the data generated by the GAN and the distribution of real data. And how do we capture it? How do we do this task is pretty interesting. So the whole research side of the people are trying to do the same thing. And there are quite a few approaches and proposed methods. And we will discuss two main ones. The one is minimax loss, which was first introduced in 2014 in original paper. And the another one is non-saturating GAN loss, which was proposed in 2017 and tries to correct the problems which was with the minimax loss. A GAN can have two loss functions at the same time, one for generator training and other for discriminator training. And how can two loss functions together is pretty magnificent. In the loss schemes, we should understand that a generator can only affect one term in the distance measure, the term that reflects the distribution of the fake data. So during generator training, we drop the other term, which reflects the distribution of the real data, and generator tries to control the other term during its training. So this is the min-max GAN loss. Minimax refers to an optimization strategy in two-player turn-based games for minimizing the loss or cost for the worst case of the other player. So for the GAN, the generator and discriminators are two players that take turns to involving updates to their model weights, as just we described the two-player game. The min and max refers to the minimization of the generator loss and the maximization of discriminator loss. As stated above, the discriminator seeks maximize the average of the log probability of real image and the log probability, inverse probability for fake image. The generator, on the other hand, seeks to minimize the log of the inverse probability predicted by discriminator for fake image. This has the effect of encouraging the generator to generate samples that have low probability of being fake. The main problem was that if generator was becoming too good, discriminator was not able to operate correctly. And the whole loss was becoming saturated, as described. And that is why there was proposal of non-saturating loss. It is a subtle change that involves the generator maximizing the log of the discriminator probability for generating images instead of minimizing the log of the inverted discriminator probability for generated images. So to simplify this subject, previously generator was trying to generate images that was less fake, and now it tries to generate images that is more real. The same task, but different approach. So this results better gradient information when updating the weights of the generator and a more stable training process. In practice, this is also implemented as a binary classification problem, like the discriminator. Instead of maximizing the loss, we can flip the labels for real and fake images and minimize the cross entropy. I know that it can get pretty boring talking about just math without real life applications. So I brought some real models which operate in everyday life. So when we talk about the generative adversarial network, I think almost all of us have heard about super resolution. This is used to enhance the quality and resolution of the photographs. Super resolution GAN applies a deep network in combination with an adversary network to produce high resolution images that we can see on this slide. So left one was the original and the right one is already upgraded by our generative adversarial network. So during the training, a high resolution image is downsampled to a low resolution image. And usually they used Gaussian filter and some kind of air factor during downsampling. And again, generator upsamples image to super resolution. We use discriminator to distinguish the high resolution images and backpropagated generative adversarial networks loss to train the discriminator and the generator. The concept is quite simple, similar to the original proposal, but the result is magnificent, as you might have seen. Second example of using GAN is in real life is cycle GAN, which was proposed in 2017. Once trained, you can translate an image frame or image from one domain to another domain. It is widely used for object transfiguration. For example, when trained on these zebras, zebra dataset, if you give it an image with a horse in the ground, the cycle GAN can convert the horses to zebras with the same background. Also, it is usually used for style transfer. If you have ever imagined what would site look like if Van Gogh or Monet had painted, you don't need to imagine anymore. You can use style transfer GAN, cycle GAN, to just train your neural network on a Van Gogh's painting and then um, feed the original site into the generator, and you will get the style of the Van Gogh or your favorite painter. To achieve image translation, the authors of CycleGAN used a very simple and yet effective procedure. They made use of two GANs, the generator of each GAN performing the image translation from one domain to another. To elaborate, let us say the input is X, and then the generator of the first GAN performs mapping X to Y using some G function. Thus, its output would be Y equals to Gx. The generator of the second GAN performs inverse mapping. So if the previous one was mapping from X to Y, it maps from Y to X, resulting in the X equals to Fy. So each discriminator is trained to distinguish between real image and synthesized image. And as we can see on the example, here we have two GANs, one trying to generate horses from zebras, and the second one is trying to generate zebras from horses. And just a little bit deeper dive into cycle GAN, because I really like this approach. To train the combined GANs, as I said, there is two GANs working at the same time. The authors added, beside the conventional GAN adversarial loss, a forward cycle consistency loss, the left one, and a backward cycle consistency loss, the right one. This ensures that if an image X is given as an input, after two transformation, we would get the same image. So in that way, we want to enforce the intuition that this mapping should be reverses of each other and that both mappings should be bijections. Okay. And my favorites, TACGAN. This is one of the best type of model I have ever worked with. This is fairly new. It was proposed in 2017 as well. And this given a pretty solid idea as to the basic concept. A concept that is pretty neat and remarkably similar to how many artists, let's say painters, work. Take your idea, turn it into a sketch, and then start adding details. That is how stacked generative adversarial network work. They take text, description of the image as an input, and turn it into the stage one, which is sketch, fairly low resolution, and then interpret this low resolution sketch into an image with details, therefore high resolution image. Let's discuss the first example where we have a text. The bird is blue with white and has a very short beak. If you were in the place of gun, what would you do? There is no any additional details, and your imagination is the only limit. So what this Tekken did is created little sketch, which is quite similar to the description, and then transfers the low resolution image in quite believable image of bird based on the description we provided. The working architecture of it is even more amazing. A low resolution image is generated using stage one. Um, there is quite multiple stages you might have seen. Stage one is GAN, the generator, and there is stage two generator for creating high resolution image conditioned on the low resolution image, and the corresponding text description. The module architecture of this tag gun consists of mainly the following examples. So first is embedding, converts the input variable length text into a fixed length vector. In the paper, pre-trained character level embedding was used. The second one is conditioning augmentation, which transfers the vector already into the digestible chunk for stage one generator. Then stage one generator creates a 64 by 64 image based on the input it got. There is also stage two generator, which transfers the low resolution image to high resolution image as well. And of course, there are stage one and stage two discriminator, which make sure that both generators are trained perfectly. The overall result is 256 by 256 images, which, as you might have think that it is quite low resolution, but the problem is it is quite computationally hard to process this type of information, and the paper was written on these parameters, but we can always upgrade it and get better resolution. And let's dive into the real world application where generative adversarial network can be used or should not be used. So the trick, the neural network itself compromise the intent working of the algorithm. Uh, this is turn can result the unwanted information being disclosed when used by hackers. So what I mean is, in some cases, hackers might hide information into images that is quite hard for human to analyze, especially when he or she is in rush. And generative adversarial network can be used for analyzing images and creating corresponding images which does not contain the information we don't want to get shared. This is not this is not, of course, only with images. It can be with the text files and documents and other type of data as well. The second, the most used approach, most used field where we use generative adversarial network is improving healthcare. In some cases, generative adversarial network can create molecular structure for the drugs that can cure or imitate at least some kind of a solution to problem. It was widely used while fighting against corona, and I remember a few companies even invited data scientists and people from different fields to donate their computational power for their models while fighting COVID. So it can say that it found already its work in real life. The third example is improving marketing strategies. It is quite good to understand what the user want and find the similar thing in our offers and offer the user what they really want. This allows the marketing team to have more customer or customers for extended period of time. And last but not least, my favorite, which I just started working on, offer generation. So instead of finding offer which we already have in database or some packet, why don't we create offer based on the user? Of course, in some limitations. So if person like, for example, alcohol, we can generate offer for him specifically for his needs. Of course, coin has two sides. There are potential challenges that might worsen our present. Deepfake is already used in many cases. All of us have seen different footage of this model, and I think we agree that it is magnificent and frightening at the same time. It might seem that it is just fun application, but in reality, it has caused already millions of dollars lost for different companies. And other than this, there is fake news generation, which is another topic that guns are used for. We have talked about creativity automatization previously, and some people took it to the next level and create interesting models that can manipulate NLP with gun and create quite believable fake topics on subjects that are sensitive for people and cause quite a lot of destruction. Of course, this should not and is not enough challenge for us to stop working on the gun. On the contrary, this motivate us to create models that can detect similar problems and solve them. So the thing is, defense should be one step forward than the challenges and attacks from the general adversarial networks. Okay, before we finish, I just want to remind you these people and tell you that none of them are real. I used application called thispersondoesnotexist.com, which use style gun. Actually, those are the real inventors of the generative adversarial network, or at least three of them. As I said, there are six inventors. And with this, I just want to show you that no matter how believable information is, just double check. We are living in strange time and guns are getting even better. So thank you for your attention. There are the credits and materials I used for my presentation. Thank you for your time.